This is the last lecture from Chapter 5, and this will focus on a couple of different things, primarily Dalton's law of partial pressures, some gas stoichiometry, where we will use our new conversion factor that 22.4 liters of any gas contains 1 mole of gas particles. And then we'll talk about different types of gas movement called diffusion and effusion. So let's start by talking about Dalton's law. Dalton's law comes into play when you have mixtures of gases. I mentioned earlier in the beginning of the chapter that all different types of gases mix homogeneously. So it's not like liquids and solids where they have to be compatible. All gases are compatible with each other, basically because they're so spread out that they don't experience intermolecular forces between different gas molecules. So anyway, they're all compatible, and because of that, we can come up with Dalton's law. And basically, Dalton's law tells us that you can calculate the total pressure of a mixture of gases by measuring the individual pressures of all the gases that make it up. If there were interactions between these gases, it'd be a lot more complicated. But it's as simple as adding up the individual pressures of each gas, which when they're in a mixture, we call them partial pressures. And so here's Dalton's law in formula style. And of course, there are a couple of different things you can solve for using Dalton's law. One would be if you were given partial pressures of a bunch of gases in a mixture, you could add all those together to get total pressure. And another way to use it would be if you're given total pressure, which if it's under normal conditions, that would just be atmospheric pressure, typically. So it'd be close to 1 atmosphere or 760 millimeters of mercury. And you could use that total pressure to calculate individual pressures of gases that make up a mixture. So let's look at a couple of problems. It may be a little bit trickier to visualize calculating the partial pressure of something. So let's see, typically, let's say we're doing the partial pressure of some component gas we'll call P sub x. You can find that if you know the mole fraction of that substance in the mixture, and you multiply the mole fraction times the total pressure, which again, under normal conditions, is typically simply atmospheric pressure. So what this basically tells you is that the partial pressure of a gas in a mixture is directly proportional to its mole fraction in the mixture. So what is mole fraction? Well, fraction of anything means part over whole, right? And so if we're asking about or talking about mole fraction, we're talking about the number of moles of that component, we're calling it X in this case, over the total moles in the mixture. So let's look at a problem doing that. All right, here we go. So let's kind of label. We got to learn some problem-solving methodology. Let's kind of label as we read what things are. The partial pressure of nitrogen, okay, so that's N2, right, is 592. So I'm going to write that as, usually if you're talking about partial pressures, it's big P and then the little subscript for the molecule or element it represents. So the partial pressure of nitrogen is 592 torr. Atmospheric pressure is 752 torr. Now, the key here is to recognize that atmospheric pressure, as I mentioned in the last slide, typically is the total pressure. It's the pressure of all of the gases that make up the atmosphere, right? Now, this problem is asking for mole fraction of nitrogen, and we usually represent mole fraction with a big curvy looking X, which we call chi. So we're looking for the mole fraction of nitrogen, okay? We just had a formula that relates mole fraction and pressures of gas, and it was that the pressure of any individual gas, in this case nitrogen, equals the mole fraction of nitrogen times the total pressure. So let's work that out on the next page using this formula. Okay, I'm going to write the formula again, or here, we can just look at here. So pressure of nitrogen is mole fraction of nitrogen times the total pressure. Okay, let's just plug in what we know. Partial pressure of nitrogen is 592. We're solving for the mole fraction of nitrogen, so we don't know what that is. And the total pressure, again, atmospheric pressure, is 752. Now just solve for the mole fraction. Divide both sides by 752. And when you plug that in, you don't get this value. That is a mistake. And instead, you get 0.787. Now, mole fraction has no units, just like any fractions, the units cancel. But here is your answer. Here is a more challenging example that combines the use of Dalton's law. Now you might want to write yourself a little note that anytime you have a mixture of gases, in this case methane, nitrogen, and oxygen, it's likely you're going to use Dalton's law, okay, which means total pressure is all the individual pressures. So in this case it'd be pressure of CH4 plus pressure of nitrogen plus pressure of oxygen. But I want you to realize first that you don't have a mixture to begin with. These little X's represent kind of valves in the lines, and they start out being closed. So to begin with, you have three individual gases in three separate containers. Okay, then when we open the valves, all of the gases will be free to move throughout the three containers. So what have we done to volume when we have opened these valves? The volume for all three gases will now be the same, okay? So the second volume or the new volume, whatever, will be 4 plus 1.5 plus 3.5, okay? And so the new volume will be 9 liters. So kind of keep that in mind. So you've changed volume when you open the valves. What else is going to change in response to volume? It will be pressure, right? Since all of these gases have a larger volume, pressure should go down. So where do we start here? We start by figuring out the new pressure of each of these three gases once we open the valve, okay? We start out with finding the new pressure of each of those gases. So let's look at how we do that. Since we are changing volume and as a result pressure changes, we're going to use Boyle's law, okay, which is P1 times V1 equals P2 times V2. But you have to do it for each of the three gases individually. So let's look at methane, CH4, first. If you go back to the drawing, you'll see that P1, the initial pressure of the methane, was 2.7 atmospheres. And originally that methane was in a 4-liter sealed container, so that's V1. We're trying to solve for the new pressure for CH4. And the new volume, once we open all those valves, is going to be 9 liters. When we then solve for P2, we find that the new pressure for CH4 is 1.2 atmospheres. And as a matter of fact, it's gone down, which is what you expect when you increase volume. When you do that same Boyle's law calculation for the other two gases, you can find the new pressure for all of them. The pressure for all of them has dropped. Now look back at the problem. The problem asked you to find the new pressures for all the gases, but it also then said what is the new total pressure. That now is Dalton's law, where you add the pressures of all of the individual gases. And that is right here. So if you add all the new pressures together, you get that the new total pressure is 2.26 atmospheres. That is likely to be an extra credit type question. I don't mean that for all Dalton law problems. I mean that in particular for this one because it's a combination of multiple gas laws that you're going to use. All right, so let's go for another application of Dalton's law. And this one, make a note, please, that it's likely to be a free response on your next exam. And it can be a little tricky, so you may have to listen to this a couple of times. The first thing you need to be able to do is understand what vapor pressure is. Vapor pressure refers to the pressure exerted by gas molecules that float around above a liquid surface. So here's a container with a bunch of liquid molecules in it, and even though it's a liquid, there will be, over any liquid, a few gas molecules that kind of hover over the surface of the liquid. So these gas molecules over a liquid, of course, like all gas molecules, will exert pressure, and we call that pressure vapor pressure. So vapor pressure refers to the few amount of gas molecules you have over a liquid surface. It's important to understand the variables that can change vapor pressure. Like any types of gas pressure, the more molecules in the gas phase you have, the higher the pressure. So how can we get more gas molecules, more of the molecules in liquid state to escape into the gas state? What might make that happen? Well, temperature is probably the most important one, okay? So as temperature goes up, vapor pressure certainly goes up too. Temperature makes more vapor, more gas phase, and therefore more pressure. It also depends on the boiling point of the liquid, okay? So if you have a liquid with a very low boiling point, what does that mean? That means it's easy to boil, right? Something with a low boiling point, easy to boil. So that might be like rubbing alcohol. You've probably noticed if you spill rubbing alcohol out on a desk that it's going to evaporate pretty quickly. So alcohol has a low boiling point. For something that has a low boiling point, it is going to have a high vapor pressure. So think of vapor pressure as the number of gas molecules. Something with a low boiling point will have a high vapor pressure. Something with a high boiling point, something that's hard to boil, will have a low vapor pressure. It's not going to have very many molecules in the gas phase. So we say that vapor pressure is indirectly proportional to boiling point. Boiling point vapor pressure indirectly related. As one goes up, the other goes down. Okay, why do we care about vapor pressure? Because there's a very common type of problem using Dalton's law, and you have to be aware of vapor pressure. And that example is if a chemist creates a gas through a chemical reaction. As you can imagine, it might be tricky to collect that gas. And so a real common way to do it is to hook a tube up to the reaction container, run that tube through water, and release it into another container, okay, that's immersed upside down in water. And as the gas enters, the water that was in that container leaves, okay, and we can measure, we can quantify and see how much gas we've made. The one with that, the one complicating issue, is if you do collect a gas you've made over water, it turns out that that gas is contaminated with water vapor. So we need to know how much of the gas mixture we have is water vapor and how much is the gas we've tried to collect. So there's some calculations to do with that, but the bottom line, the most important thing for you to realize, if you do collect a gas over water, you must subtract the vapor pressure of the water from the total pressure of that mixture, which again is atmospheric pressure, okay? So that's what the first thing we're going to do in this next example. And a reminder again, this is a typical problem that you will see for one of your free response questions. So pay close attention, make sure you understand. All right, so I told you that what you're probably going to have to do is, first of all, realize Dalton's law. It says total pressure equals pressure, and the mixture we have in this case is water vapor pressure, and then the pressure of whatever the other gas is that we're collecting. Okay, and this is for when you collect gases over water. So obviously you need to know the pressure of water. That's simply the vapor pressure. And the vapor pressure of water is going to vary depending on the temperature. So you're going to have to, the problem will always have to give you the temperature. Let's just say they said it was 25 degrees. We would then look at this chart and say, okay, vapor pressure of water at 25 degrees is 23.78. And then you would have to take that into account to figure out the pressure of the gas. So let's go ahead and do that. Here's an example. They are collecting dinitrogen monoxide gas. They're collecting it over water. So that means the first thing we need to do is subtract vapor pressure of water. Subtract vapor pressure of water from the total pressure, which is the atmospheric pressure. Okay, so let's just go ahead and do that first. They gave us total pressure. They could have just said the atmospheric pressure is 0.928. And so what do we have here? Let's write Dalton's law again. Total pressure is the pressure of all the gases. In this case, we have water gas, water vapor, and we also have dinitrogen monoxide. All right, total pressure is the atmospheric pressure, so 0.928 atmosphere. We look on that chart. Well, in this case, I told you the vapor pressure of water at 22 degrees is 21 torr. So we know that pressure of water is 21 torr, and we're trying to solve for or figure out the pressure of dinitrogen monoxide. I'm hoping that you notice now that you have an issue, and that is the units are different for pressure. So we have to get both units in either torr or both units in atmosphere. I'm going to go ahead and get it in atmosphere. That's just the more common used one. And so let me see what that is. If I have 21 torr and I want to convert it to atmosphere, I have to remember that there are 760 torr in 1 atmosphere. And so 21 torr divided by 760 is 0.0276 atmosphere. So that is pressure of water vapor at 22 degrees. So now I'm going to go back to Dalton's law, and I'm going to solve and see what pressure of N2O is. All right, so pressure of N2O, we just said the atmospheric pressure is 0.928 atmosphere, and the pressure of water, once we converted it into atmospheres, is 0.0276. And when we go ahead and do that, we get that the pressure of N2O, partial pressure of N2O, is 0.90 atmospheres. So you might think, okay, yeah, I figured that out, I'm done. You're not really, because if you go back to the question asked you not what the pressure of N2O is, but what the volume of N2O is. So now you have to remember, how do you get from pressure to volume? And they're also talking about moles. So hopefully you thought of the ideal gas law, PV equals nRT. And if we rearrange that to solve for volume, which is what this problem is asking for, it means you divide both sides by P, right? And you end up with volume equals nRT over P. And then you plug in what we know. The problem gave you moles, which is 0.032. Hopefully, by now you're kind of memorizing the gas constant, which is 0.08206. Remember, the units for this form of the gas constant are liters, atmospheres divided by moles, Kelvin. That just means that all the units of the other things in this equation have to match the R unit. So your volume is going to be in units of liters because of the R value. Let's see, temperature is 295. They gave us 22 degrees Celsius, so we have to convert it to Kelvin. And so 295 Kelvin. And then we divide all that by pressure. And we figured out pressure, the corrected pressure, just the gas, it's 0.90. And when you crunch all that out, you get that the volume is 0.86 liters. Kind of a complicated problem. So there are worksheets. If you haven't started working them already for the gas laws, please, please, please do, and do a bunch of them this weekend, especially of this, because this will be a free response type problem. Okay, now we have a couple more topics in this last pre-recorded lecture, and we're going to talk a little bit about stoichiometry when you have gases involved, and then we'll talk about how gas molecules move at different speeds across space. So as far as stoichiometry, I've introduced this before. It's kind of a mole map, and just to kind of remind you, we have converted in the past between moles and molecules or atoms, which we call particles, right? We've also converted back and forth between moles and grams. Hopefully you remember that when we convert between moles and particles, we use Avogadro's number, 6.02 times 10 to the 23rd. When we convert back and forth between grams or mass, we use the molar mass of the substance from the periodic table. And what's new is we can now convert between moles of a substance to volume of the substance if and only if it's a gas. Okay, so if you have a gas and you're at STP conditions, the conversion is that 22.4 liters of a gas equals 1 mole exactly. So that will be a conversion factor you need to be very familiar with. And let's do a sample problem. How many grams of water, so we're looking for this, right? How many grams of water form when we have 1.24 liters of oxygen gas? So we have to get from liters to grams. So if you remember the mole map I just showed you, so we are starting at liters, so we're starting up here, volume with liters, and we're trying to get to mass. So we have to go to moles, everything goes through moles, and then we have to do a mole ratio because we're comparing two different substances. And then we have to convert to grams. So let's look at that step by step. If you think there's any chance you can do it on your own, go for it, please. But I will go over the solution on the next slide. All right, so as I said earlier, as always, start with the given, which is 1.24 liters. It's important to write not just that it's liters, but liters of what? Because when you have a chemical reaction, there are several different substances. You need to keep them straight. Our new conversion factor, if we're in volume and it's a gas, which it is, the first thing as always you do is go to moles. There are 22.4 liters in 1 mole. And that's true only at STP, which this problem mentions. Once you are in moles of H2 gas, remember we're trying to get to moles of water. So now you need the mole ratio, which shows the relationship between moles of hydrogen gas and moles of water. That's when you look at the balanced equation at the coefficients, and 2 moles of H2O is made from 2 moles of water. All right, and let's see. If you were to stop here, you would have moles of water. The problem's asking us for grams of water, so we have one more step. That's the molar mass, taking some moles of water to grams of water. When you plug all that in, you get that 0.998 grams of water can be made if we start and react all of 1.24 liters of hydrogen gas. So the only thing that's new here is the gas conversion. So the very last topic that we're going to go over is the speed at which gas molecules travel through space. Okay? And that depends primarily on the molar mass of the gas particle. And so I've always kind of thought of football players when I think of this. That's not always the case, but usually if you have very large or high molar mass objects, they don't tend to move quite as fast as the smaller ones, and that is true with molecules. So basically, as molar mass goes up, the velocity or speed that it moves throughout space goes down. You can ignore that. Here's the equation that shows you that. You don't have to worry about it. They get fancy and call it root mean square speed. You don't have to worry about that. But the bottom line is just think of velocity of a gas particle for this fancy thing. It's proportional to the square root of the inverse of molar mass, okay? So again, you're not going to use one quite this complicated, although I must say I've seen this equation, the ACS final ask you to use this. It's not a big deal. In case you see it, just for those of you who want to get an A and everything, the numerator is simply 3 times the gas constant times temperature in Kelvin divided by the molar mass of the substance, and then you remember to take the whole square root, and typically they give you that formula. So anyway, but I'm not going to give it to you. Let's look at what I might give it to you. Let's go over a couple of definitions before we go over one more gas calculation formula. All right, we will be talking about effusion and diffusion. So effusion is the escape of gas molecules through a tiny hole. So when you get a hole in your tire, for example, that would be effusion. Obviously, that's going to be a little bit slower than other types of gas moving, or limited, I should say. And it turns out that kind of complicated equation I gave you 2 or 3 slides ago, that had 3RT, square root of 3RT over molar mass, whatever, that if you take the ratio of 2 different rates for 2 different gases, all of the numerators cancel out and you end up with this. So this is Graham's law. So I want you to look at it for a minute. It'll kind of help you remember. So if you're comparing the rate of effusion, or it could be diffusion, which we'll talk about in a little bit, to gas 1 divided by the rate of effusion for gas 2, what do you notice about the right side? Remember the relationship between rate or velocity and molar mass is inverse. So notice now that the molar mass for the first gas is in the denominator, and the molar mass for the second gas is in the numerator. So it's crisscross, inverse relationship. And that's probably the most common error that students make, is they forget that. Also, please remember that this whole ratio of molar masses has a square root on it. And so also students will tend to take this ratio and then forget to take this square root. B. There are also concept type questions that you'll be asked where you don't actually have to plug through Graham's law and calculate, but you need to be aware of it to answer the question. So for example, what if I asked you to compare the effusion rates of, let's say, hydrogen gas versus nitrogen gas? Well, hopefully you would remember that as molar mass goes up, the velocity goes down. So nitrogen has a higher molar mass, so you hopefully would expect it to have a lower velocity. Okay? And hydrogen has a very low molar mass, so it should have a higher velocity. So if you have one balloon filled with nitrogen, oh, it's supposed to be helium, sorry. Nope. Okay, same thing. and another balloon filled with helium, and you have a little hole. Well, you even have little microscopic holes, because these type of balloons, the latex balloons, are made up of little holes. So, as you know, over a period of hours, any gas that you put in a latex balloon is going to start escaping. But which gas will escape faster, nitrogen or helium? Helium will. Okay, helium will escape much faster because it's much lower molar mass. It's a smaller molecule, so it's going to make its way out of these pores or little microscopic holes in the balloons, and so the helium balloon will deflate faster. That's why we have our great mylar balloons typically when we're going to have helium balloons. They'll last a lot longer because mylar has much smaller holes than the latex does. All right, let's talk about diffusion for a minute before we do a calculation. Diffusion is simply the spreading out of a gas. So if you have a bottle of perfume that you open, the perfume molecules, some of them are going to escape into the gas phase. That's vapor pressure, right? And they're going to diffuse throughout the room or whatever space they're in, because they don't have to go through a little hole. All right, so finally, here's an example that's going to require you doing a calculation using Graham's law. So let's just write Graham's law up here. The rate of effusion of one gas divided by the rate of effusion of the other is equal to the square root of inverse molar masses. If you read this problem, the whole trick is sorting through the words of the problem and knowing what goes where. So if we have a gas that effuses 3.2 times slower than helium, there are a couple different ways to set this up. The way I like to set it up is to say helium is 3.2 times faster than the unknown gas, which we'll call X. Okay, so the rate of helium effusing is 3.2 times faster than the rate of our unknown compound X. So what do we do with this? Going back to Graham's law, that means that I'm going to go ahead and put helium on top. It doesn't really matter. But I'm going to put, for helium, 3.20 times the rate of X, that's what I just determined here, over whatever X is, the rate of X, okay, equals, now remember the top was the rate of helium, okay, so the molar mass of helium goes in the bottom here. They've got to be diagonal from each other, and the molar mass of helium is 4. We're trying to solve for the molar mass of this unknown compound X. So let me rewrite what we have so far. Okay, so how do we solve this? Well, we can cross out what's the same on top and bottom, that's just algebra, and rewrite it as 3.2 equals square root of molar mass of the unknown gas over 4. How do we get rid of this square root sign? Square both sides. Okay, and so now we end up with 3.20 squared equals simply molar mass of the unknown over 4. 3.20 squared is 10.24 equals molar mass of X over 4. And then finally, let's see, molar mass of X would be 10.24 times 4, which would be 40.96 units per molar mass or grams per mole. Okay, so go ahead and make sure you're comfortable with mathematical simplification. You don't have to do it my way. There are several ways to simplify that math. But think through and make sure that you can work a problem similar to this. Here's a very challenging example. If you feel like you understand these problems, go ahead and give it a try. If you feel like you're still kind of lost, then you might want to just listen to me work my way through it. I'm trying to think of different ways you could get thrown off with a Graham's Law problem, and this is another way. Oftentimes the problem, rather than giving you rates, because remember you need the rate to do Graham's Law, will give you a time. Think about the rate you know, miles per hour. So if they give you time, that's the inverse of rate. So how do you get rate if they're giving you time? The rate of diffusion is going to be moles, in this case moles per minute. It's how much in how much time, how much stuff moved in how much time. So in order to get the rate of NH3, you would have to do an initial step, which is 0.00251 moles in 2.47 minutes. And that would give you the rate of effusion. So you'd have to do that first before you plug into Graham's Law. So if you do that, you get that the rate of, it's effusion, is 1.02 times 10 to the minus 3. Now you can use Graham's Law. So if you put that on bottom, the rate of ammonia on bottom, that means the molar mass of ammonia goes on the top. The molar mass of ammonia is 17 grams per mole. And we're comparing it to HCl, hydrochloric acid. So if we put that on top, it doesn't matter which one you put on top and bottom as long as you have the crisscross relationship. The molar mass of HCl is 36.5 grams per mole. And so we are trying to solve for the rate of effusion of HCl. So mathematically, again, please make yourself, if you haven't done this problem on your own, try to make yourself simplify that mathematically on your own. That throws people off, and typically the first thing to do would be to square both sides, okay? And that gets rid of your square root. So go ahead and try it, and hopefully what you end up with is you will solve for the rate of effusion of HCl, which you should get 4.76 times 10 to the minus 4. The problem is asking you, though, how much HCl. That means how many moles of HCl would get through in the same amount of time. And so remember, your rate is moles per minute, so if you want to just get moles, you've got to multiply by minutes. Kind of do the reverse of what we started to do in the beginning. These are tricky problems, y'all, okay? So definitely the first thing to do is work with the simple gas laws and the ideal gas law. Get really comfortable with those, and then begin to tackle the trickier ones like Dalton's law and Graham's law. And the very last thing I want to leave you with from Chapter 5, we've been talking about ideal gases. I'm hoping you remember. If you don't, you need to now. An ideal gas assumes that there are no intermolecular forces between gas molecules. They don't even know each other exist. And I'm mentioning this because it'll make more sense as I discuss non-ideal gases. But also one of the assumptions in the kinetic molecular theory, which we covered on the first day, intro to gases, is that the gas molecules themselves take up negligible space. And that's because there is so much distance between gas molecules that most of the space is simply empty space, and that the volume taken up by the gas particles themselves is negligible. So remember that ideal gases are favored under only certain conditions, and those conditions are high temperature and low pressure. So if you remember Corey's, and he said totem pole. Temperature is high, pressure is low. So those conditions favor ideal gas behavior. And so if pressure gets high or temperature gets low, you're going to start condensing and having non-ideal behavior. We call that real behavior. And then things get really complicated. So what I have decided to do, because real gas behavior, the formula The gas law formulas get very complicated. I just feel like you don't need this right now. It's not as important. So I think what I'm going to do is I will add a bonus question on the next exam over the behavior of real gases. And I have a couple of slides on here by it. But the bottom line is, if you have a non-ideal gas, in other words, a real gas, what's going to happen is the pressure of the real gas, the non-ideal gas, is going to end up being less than the pressure of the ideal gas. Remember, what causes pressure? Pressure is due to collisions of the gas molecules against a container. So with a real gas, that pressure is actually going to be less, okay? So if you think about the conditions that favor non-ideal gases, low temperatures, the gases are going to start to condense. There are going to be less collisions against the wall, and that's why the pressure is lower. Okay, and so to conclude, a real gas will tend to have higher volume. Remember, I just said ideal gases, we almost assume their volume is about 0. But if it's a real gas, gas molecules take up volume, and they're going to end up having lower pressure for the reason I just mentioned. And so look what happens to the ideal gas law. Okay, it gets pretty, it starts out here, it gets pretty complicated, doesn't it? So let me show final. Here we go. Here's the overall corrected ideal, well, non-ideal gas law. This is how complicated it gets. So I would never give this to you on a standard test. These little factors that are new, A and B, those are the correction factors for pressure and volume, and they're measured by physical chemists for every single gas. And so you would just plug the A and B values in. I'll give you a bonus question on this, but please don't worry about it until you have all of the other gas laws worked out and you're real comfortable with them. That's it for Chapter 5.